Hello and welcome, class, to a brand new chapter. We are starting chapter 12, so we've just finished talking about gases in chapter 11. Chapter 12 is all about what we call the condensed phases of matter. So these include liquids and solids, and by the end of chapter 12, we're also going to be talking about phase changes. So let's start with the phase that is closest to gas, liquid. All right, so we've spent a lot of time talking about gases, but what really are the qualitative differences between liquids, solids, and gases? How can we better put into words what these different observations are? All right, so the two main observable differences between the different phases of matter are what shape they take and how their volumes can be measured. So let's talk about shape first. So if the shape of your piece of matter is indefinite, meaning that it can be molded into a different shape, or rather it cannot hold its own shape, then we are going to be working with either liquids or gases. So this makes sense. Liquids obviously fill the base of their container. So if we're looking in this flask, for instance, we can see that the liquid has all spread out. It's all pooled at the bottom of this Erlenmeyer flask in the illustration, and gases have even less of a definite shape because they always spread out to fill the whole container. So whatever the shape of your container, this is going to, statistically speaking, be the shape that your gas is also going to spread into. The only phase of matter, the only state of matter, at least of the states that we're going to be talking about in general chemistry, that is able to hold its own definite shape is the solid. So regardless of how much solid there is, it's always going to hold its own shape, even regardless of the container. So we can see that the red mass here is definitely in a lump inside of the container. It's not flowing to fill the bottom. It's not, escaping to fill the entire container. It's just its own definite solid chunk of stuff. So what the volume pertains to is how we can measure the volume of our object, our state of matter. So gases have indefinite volumes. Again, this is because gases spread to fill out their entire container. So we can assume not only the shape of the gas is going to equal that of its container, but also the volume of the gas is going to equal that of its container. So we can condense gases down into smaller spaces. We can allow them to expand into these larger containers, like what is illustrated here. But suffice to say, the gas has no definite volume on or unto itself. Solids and liquids, however, have their own definite volumes. A solid and or a liquid will take up a specific amount of space that is measurable and will also be consistent. So for example, if the liquid in this center container, let's say, is 100 milliliters, and we transfer it out of this flask into, let's say, a beaker, inside of this beaker, it's still going to be 100 milliliters of the solid, or of this liquid. So the solids and the liquids will maintain their own specific volumes, irrespective of the type of container that they're held in. So solids have definite shape and definite volume. Gases have no definite shape nor a definite volume, and today we're going to be talking about the liquids, the things that have an indefinite shape but do have a definite volume. And today we are going to be talking about liquids. All right, so by technical definition, liquids are substances that flow freely but still have a definite volume. So this is the big difference between liquids and gases. Both are able to move, both have an active kinetic energy about them. This is how their internal energy is able to manifest, is through kinetic energy. However, liquids are more condensed and have definite volumes, due to the presence of intermolecular forces. So the big differences between gases and liquids are due to the molecules' abilities to attract or repel one another in the liquid case. So this is what we can see in the diagram on the right here. Each of these molecules are, H, F molecules. So we have definite dipole moments, a partially positive charge on the hydrogen, a partially negative charge on the fluorine. And in this key down below, we can see that the attractive forces between molecules are highlighted in green. The repulsive forces are highlighted in gray. So there is attraction present between the partially positive and the partially negative. There is repulsion between the similar charges, the negatives, as well as the positives, like we can see here. And so the balance of the attraction and the repulsion between these polar molecules, these molecules with definite dipole moments, is what leads to the combination of their ability to flow freely due to the repulsions that are actively acting on the molecules, pushing them all around in different directions, as well as the condensed phase, the definite volume, is the result of the attractions. So gases don't have these attractive and repulsive forces acting on them. I will admit, particular real gases, right, if we're assuming real behaviors, not ideal behaviors according, like how we talked about in chapter 11, there is definitely a little bit of a gray area between gases and liquids. Some gases will have more liquid behaviors, some liquids will have more gaseous behaviors or properties, but in general chemistry, we are going to assume that there is going to be a hard boundary between them, this nice binary. Gases will behave ideally. Liquids will contain intermolecular forces between molecules. All right, so the presence of these intermolecular forces holding the molecules in place at closer distances than what are experienced in the gaseous state lead to a number of really interesting properties, such as surface tension, viscosity. There are a couple of others that we're going to talk about today as well. So without any more preamble, let's just jump straight into these unique properties that liquids have. The first of the properties that we're going to talk about that are unique to liquids, that gases do not have these, is surface tension. So by definition, surface tension is the energy needed to separate molecules at the surface of a liquid, right? It's how tensely these molecules are being held together. The molecules that are being held together are held together by intermolecular forces. So we're going to talk about the droplet here on the right first. So this water droplet, which is what the label here says, this little bubble is, it's just a little water droplet. Contains a large number of molecules. Now, obviously, this diagram is not to scale. Droplets contain hundreds of millions of quadrillions of molecules, all depending on exactly how large the droplet is. So these molecules in this picture are definitely blown up just to be able to see them a little bit better. All right, so let's talk about the inner molecules first. So each of these inner molecules is going to be attracted to another molecule through intermolecular forces. That is what all of the arrows as well as these lines that I am drawing represent, the attractive forces between one molecule and all of the other molecules around it. Now, as was illustrated in the previous diagram, there will also be some repulsive forces, all depending on how these polar molecules are aligning. However, the overall attraction or the overall interaction will be attractive. If it wasn't, then we wouldn't have a droplet. So the molecules in the center are held together by this kind of like webbing of other molecules around them. And we could pick any molecule in the middle, like let's say this molecule, and we'll see that that's also the case. He's surrounded by, there we go, another number of molecules around him, and all of these connections are going to stabilize each water molecule inside of the droplet. Now, the same phenomenon happens on the surface, but to a much stronger degree. Now, we can see this molecule on the surface only has attractive arrows down below him, right? It's impossible to have any attraction up on top because all that's up here is air. There's no more molecules. So what this means is that in order for our molecule on the surface to be as stable as a molecule on the inside, it's going to have to form a fewer number of stronger bonds on the surface. And that's going to happen with each of these molecules on the surface. Each of these is going to form really tight connective bonds with each other to make sure they're all held in place, to make sure they're all super stable. So what we end up with is almost like a molecular game of Red Rover. Red Rover, if you ever played that game on the playground when you were younger. The whole premise is that these if you're playing Red Rover, you're linking arms with other kids, and the opposing team is going to send someone to try and run through the line. And if your link to your partners is very strong, nothing's going to break that line, and you're going to end up winning the game. So these molecules are kind of doing the same thing, where one of these molecules is linking arm in arm with another molecule nearby and is forming a really, really tight connection. And we're going to do this all the way around the surface boundary. So the energy that is needed for another molecule, here represented by another kid or another child, to run through this line, that is going to be equal to the quantitative surface tension. Now, all depending on the shape of your liquid, exactly if it's forming a droplet or just a flat surface, exactly what the molecule is that is inside of the liquid, if there's other stuff present as well, you're going to get varying surface tensions. But the general correlation that we're looking for is the stronger the intermolecular forces between the molecules, right? The stronger the attraction, the greater the surface tension. So more energy would need to be put into the surface in order to break the molecules apart, in order to break any one of these bonds, these intermolecular forces, these attractive stabilizing forces between the water molecules. All right, so the stronger the surface tension, again, more energy it would take to break through the surface. So we can actually there are some pretty cool real world results of surface tension, like of other materials interacting with liquids. So we can see here on the left-hand side a pretty cool phenomenon that certain items like pins or even like insects, small animals like lizards can spread out their weight. They can distribute their weight on the surface of the water. And if they distribute their weight, what they're really doing is distributing their downwards force. So there is going to be a lesser degree of downwards force on the surface because we are increasing our surface area. If we're thinking back to the relationship between forces, surface areas, pressures, stuff like that. So if we're distributing our weight, that means that we are not going to apply enough energy to break through the surface, right? We're going to lose that game of Red Rover. This kid now representing the pin is not going to be able to break through the surface because not enough pressure is actually being applied, not enough energy is being put in. And so the pin is able to lay on the surface of water, which is what we can see down here. The pin is just laying flat on the surface of water. We can also see, if we're looking closely enough, that the water is kind of adhering to the pin. It's helping to push it up out of the surface of the water. And again, there are a great number of insects that can walk on the surface of water. There are certain lizards and birds that are able to also walk on the surface of water, and they do so by distributing their weight and taking advantage of the great surface tension between these water molecules. The next of the properties that we are going to talk about is called capillary action. So the property of capillary action is also related to how menisci, which is the plural of meniscus, this is how meniscuses, or menisci, are formed. So we actually can describe both of these two phenomenon at the exact same time. And these phenomenon are caused by a balance between the forces of cohesion and adhesion. So these two forces are somewhat in competition with each other. Competition with each other. So cohesion is an attraction between like particles, meaning that these are the same types of particles. So this would be like water interacting with water or mercury interacting with mercury. Forces of adhesion are interactions between unlike particles. So this would be like water plus glass or mercury plus glass. So we're looking at how well one material will stick to another. Literally, we're looking at how well one molecule will adhese itself to another. Cohesion is like cooperation between like particles. So it's how a molecule will be able to interact with another molecule of its own type. All right, so the balance between cohesion and adhesion are going to be what result in what we call a meniscus and a reverse meniscus. We'll talk about the menisci first, and then we'll talk about capillary action, since capillary action is really just a very extreme meniscus. All right, so on the left, what we have pictured is H2O. It's just dyed red for visibility inside of this picture. And on the right-hand side, we have mercury. So water, we'll just talk about this first, present inside of this glass tube, forms what we call a meniscus. Meniscus. Mercury, on the right-hand side, with this concave lump on top, forms what we call a reverse. Reverse, there. Meniscus. All right, so let's talk about water again. Water first. Got ahead of myself a little bit with the reverse meniscus. Okay, so water forms a meniscus, this concave shape inside of the glass container, because of the balance between its internal cohesion and adhesion. The forces of its internal cohesion is weaker than the forces experienced of adhesion. So we can actually see this literally demonstrated in the kind of zoom in section, this little picture right here. So water, made up of H2O, is able to bond attractively with the material that is making this glass. Glass, at least conventional glass, there are different types of glass, but for the most part, glass is made up of silicon dioxide. And so the hydrogens inside of the water, we can see are attracted to the oxygens in this silicon dioxide. We have these really strong, charged interactions, these electrostatic interactions, and so this water molecule is able to bond attractively with the carbon, or with the silicon dioxide here. Well, because this interaction is so strong and because charges are attracting one another, each of these water molecules begins fighting and trying to crawl over the other water molecules to get to the glass. So the meniscus that we can see on the macroscopic scale is the result of water molecules climbing over each other to try and get to the glass as best as they can. All right, mercury, we can see the exact opposite. The reverse meniscus as the result of cohesion being stronger than adhesion. And the zoom in of our concave meniscus demonstrates this as well. Mercury, which is a metal, is much more stable and well suited for interacting with other metals, and therefore want to get away from the silicon dioxide wall. So we can see these mercuries literally pulling away from the wall as best as they can, and interacting with each other, creating this sort of domed bubble instead. So the cohesion here, or the interaction with like particles when it comes to the mercury, is going to be much stronger, therefore the reverse meniscus. All right, so what is the connection then to capillary action? Well, when it comes to materials like water in this silicon dioxide container, we just said that the water molecules are trying to crawl over each other to further themselves up the wall. Well, we can use that explanation to make sense of the phenomenon, the property of capillary action. So capillary action, on it's just the surface definition, is the ability for a liquid to be pulled up into a very narrow container. So capillary action is also what leads to water being able to crawl up inside of a piece of paper or a paper towel. If you've ever just dipped a piece of paper towel inside of the glass of water, the water is going to suck up into the paper towel very quickly. It's because inside of the paper towel, we have a lot of very small, microscopic tunnels caused by the fibers of the paper. And so water is able to just travel up each of these tiny little fibers, these tiny little capillaries inside of the paper towel. So the question is, why does this happen? This capillary action occurs because each of the tubes is very, very small, and water is still trying to crawl over other pieces of water to get to the tunnel, or to get to the surface of the container. So we can almost imagine if this tube were to be, let's say, half the size, we would have water molecules crawling over each other here on the left as well as here on the right. So our meniscus would look something like this. Well, if you make the tunnel even smaller, we're going to have water molecules fighting over each other to crawl up the left and to crawl up the right. And as we continue decreasing the size of this tube, we'll eventually reach a point where the water molecules are able to not only crawl up the left, but also then immediately to jump up to the right. And we'll have this kind of back and forth motion as all of the water molecules travel up net together. So capillary action is the result of very strong forces of adhesion, stronger than cohesion, and this strong adhesive force is made even stronger if the walls of the container end up being so small that the water molecules can all just travel as a group up through the filament. Okay, we come to my favorite property to talk about when it comes to liquids, viscosity. So viscosity is the resistance of a liquid to flow. So it's almost like a measure of like how liquidy is the liquid versus how solid is the liquid. The more viscous something is, the more it's going to behave like a solid. So viscosity, again, is proportional to the resistance of a liquid to flow. This resistance is due to internal forces of friction, which are the result of strong intermolecular forces. So the greater the intermolecular force, the more quote-unquote molecular or internal friction, and therefore the more resistance we're going to have. Now, the more viscous a liquid is, the more thick and sticky this is going to become, even broaching like into, again, the territory of a solid. My favorite liquid is that of tar, also known as pitch. Tar, laid out on the road, looks like it's a solid, and that is because it is very solid-like. However, tar is, in fact, a liquid. It is able to flow, and it has a measured viscosity, or at least we're still in the process of measuring its viscosity. All right, so let's talk about the picture and the table that I have down below. The world's longest running experiment, which is still active to this day, is known as the pitch drop experiment. The pitch drop experiment is that of like tar, again also known as pitch, was poured into this funnel that we can see here in the year 1927. It was allowed to cool off for 3 years, and then they kind of cut off whatever liquid had flowed out at that point, because if a liquid is warmer, it is going to flow faster. They wanted to get this thing down to room temperature. So once they cut the stem, they started counting. How long does it take for a drop of pitch to actually fall out of this funnel? Now, they've been using this as a metric to get an idea for how viscous, like literally how quantitatively viscous this liquid is. And we can see in the table how many drops have fallen since the experiment was started. Now, the stem, again, was cut in 1930, and it wasn't until 8.1 years later that the first full drop fell. And what it means for a drop to fall is not that a drop is forming like this, but rather it falls and it disconnects. It falls into the beaker down below. All right, so since the experiment has started, there have been 9 drops total that have fallen. In the first 7 drops, we can see the average number of years was somewhere around 8 years for a drop to fall, and then suddenly there was this big increase in the year 2000. What happened in the year 2000 is that a new AC unit was installed in the building where this pitch drop experiment is taking place. Therefore, because now the room is cooler and more quality controlled, the years have increased to around 12 to 13 years in between drops falling. Now, as I said, this experiment is still being run today. The picture that I grabbed says that there's a time lapse, or this picture is a screenshot of the time lapse from 2012 to 2014. They still, though, or rather, by they, I mean the scientists who are running this experiment out of Queensland in Australia, not only are taking time-lapsed videos, but nowadays are actively live streaming the pitch drop, so that way the world can be there when the 10th drop falls here in the next couple of years. So I have a little click me down here. I've already pulled up the web page, and here it is. So you should be able to see a screen capture right now of my Google Chrome page up, and we can see, if we're paying attention to this clock down here, the clock is running. This is an active live stream. It looks like it's apparently 8 a.m. currently when I'm filming this in Queensland, Australia, and the pitch drop is forming. It's kind of sitting here at the edge of the funnel, and this is the exact same pitch, the exact same tar that was first poured in 1930. Or I should say first poured in 1927. Experiment started formally in 1930. So this is, to me at least, I know it's like super nerdy, but it's super fun. You can see that there are also 18 people right now who are around the world watching this with us. Now, we're not going to be watching for very long. There's still a couple of other properties we have to talk about. But if you ever want to check this out, all you need to do is literally Google University of Queensland, the pitch drop experiment, and you can just tune into the live stream whenever you want. Now, assuredly, the experiment itself the experiment itself is going to keep going, but the next drop, just based off of these first couple of time points, is not due to fall in the next couple of years, even though it looks, as we just saw, like there's a pretty strong bead of tar forming on the funnel. It's going to be hanging out there for another couple of years or so, unless the AC unit fails. Then we could probably expect to see it fall any day now, but the AC is, as far as I'm aware, still fine. Yeah, so there are many ways that we can measure viscosity, but what we care about right now in this class is being able to understand what causes the viscosity. So the stronger the intermolecular force, again, the more friction, the greater the resistance to flow. Tar is one of the most viscous materials, one of the most viscous liquids that we know of, and it all has to do with the intermolecular forces. So let's compare tar to that of water. All right, so tar is a substance that is actually a mixture of many different hydrocarbons. And we're going to represent this hydrocarbon as CXHY. So there's some combination of numbers down here, but each of the numbers at the very least is, greater than 18. So we have very large molecules. Now, each of these tar molecules may also contain, or rather the tar itself as a mixture may contain some certain number of impurities, but we're just going to focus on the hydrocarbon piece since this is what comprises most of the compound, most of this material. The hydrocarbons may be entirely non-polar molecules because they are comprised of non-polar bonds. However, they are very big non-polar molecules. And as we have also talked last semester, all during our intermolecular force unit, the larger your molecule, the more dispersion you can have. And the more dispersion you can have, the more tightly your molecules are going to be held together. So on the very small scale, like between very, very small molecules, dispersion doesn't really have that big of an effect. But we can see observably by the time our molecules get up to be the size of something like tar, there's so much dispersion because these molecules are so big that the material as a result ends up being very resistant to flow. So the sum of the parts here is definitely greater than what we would expect. The sum of all of our dispersive interactions, though each individual dispersive interaction is weak, the sum is very, very strong. We can contrast this with water, which, yes, water molecules are held together by pretty strong hydrogen bonds, but the number of hydrogen bonds that each individual water molecule can form is at most 6. With all depending, if you're in solid form or liquid form, that number may vary. If you're in a liquid form, the number is more than likely going to be only 2 or 3 hydrogen bonds at any one time. So Even though we have a very strong intermolecular force, there are a very few relative numbers of them per each individual molecule. This is what gives water some very unique tense properties. Like water has a relatively high surface tension, all things considered, when compared to some other liquids, but it's also not very viscous because the water molecules are able to flow past each other very easily due to the lack of the number of intermolecular forces. The last property that we have to talk about when it comes to liquids today is volatility. Volatility is the measure of how easily a liquid evaporates as a function of both pressure and temperature. So this type of volatile evaporation may happen even at a temperature lower than the boiling point of the liquid. A liquid that is very volatile, as we can see here, will rapidly change from liquid to gas, sometimes even without much prompting. So this liquid that's present here on the left, we can see like the surface of the liquid is somewhere here, here, and here for each of them, so their volumes are around the same. But this liquid here on the left is evaporating into a gas much more readily. Now what this means is that there are very weak intermolecular forces between each of the molecules in this particular liquid on the left. And because there are weak intermolecular forces, it's going to be much easier for each of these molecules to get away from each other and turn into a gas. Now, by the time we turn our attention to this non-volatile liquid on the right, we can see that there is practically no gas. Like there's none illustrated. Experimentally, we would find a very low vapor pressure here. There's not a lot of gas present above the surface of this liquid. And this is because we have very strong intermolecular forces present here. So the strong intermolecular forces are going to hold each of these individual molecules together. It's going to create a very strong surface tension. We are not going to see a lot of molecules break through or evaporate as a result. So strong intermolecular forces give you also a high surface tension. They give you a very high viscosity. And all depending on the balance between cohesion and adhesion, we would expect to see a more extreme meniscus. Either an extreme straightforward meniscus or an extreme reverse meniscus, all depending again on whether the adhesion or cohesion is really strong. With our weak intermolecular forces, we expect to see very low surface tensions. We expect to see very low viscosities, so these would be liquids that pour very, very easily. And we would expect to see very weak meniscuses. So we would not expect to see any type of adhesion or cohesion. The weaker the intermolecular forces, the flatter your meniscus is. The less likely you will have a balance or like a competition between adhesion or cohesion. If neither one is present, we won't really have a meniscus here. All right, so we've been talking fairly qualitatively thus far, kind of tying together the intermolecular forces with each of these properties, but we haven't really quantified anything. Right, we didn't quantify surface tension, we didn't quantify viscosity, we haven't quantified the meniscus, but what we are going to do is quantify the volatility. And the reason why we're going to be focusing on volatility I'm going to give two big reasons. The first is because of the partnering of scientists who worked on this problem, whose names you might remember, Clausius and Clapeyron. Clausius was the scientist who developed kinetic molecular theory, which we talked about at the end of chapter 11. He was, again, the guy who, in essence, catalyzed the breaking of chemistry off into its own field. Clapiron was the scientist who discovered and published the ideal gas law. So these two scientists came together to work on understanding the volatility of these liquids and how we can quantify how volatile exactly they are using something known as vapor pressure. So what is vapor pressure? By definition, vapor pressure is the pressure of a gas or vapor in direct contact with its liquid or solid form. So we're focusing on liquids right now, but the same definition would apply to things like, let's say, dry ice, which directly evaporates into gaseous carbon dioxide. All right, so the real world example that I have for you guys is like, or pertaining to the importance of vapor pressure is, how many of you have spilled something like a glass of water, a glass of milk, a can of Coke, whatever, like onto a surface and you just let it sit there? Like maybe you didn't let it sit there intentionally, but it evaporated all on its own. Same thing could be said for like puddles after it rains. If there is a puddle of water sitting pretty squarely inside of this like sidewalked, like paved sidewalked area, the next day, this is all going to be gone. Where did it go? One could rationalize that maybe the water like seeped down into the ground between these cracks. Okay, fine. But that doesn't explain how water would evaporate off of a solid surface like a counter where there is no chance for it to like seep into anything. How this water evaporates even without needing to get to its boiling point or without experiencing a change in the ambient pressure around it is because of vapor pressure. Above a liquid, as we can see illustrated kind of like crudely here on the right, there is always going to be some amount of gas on top of it. And the reason why there's always a little bit of gas on top just has to do with the balance of intermolecular forces. Liquids are dynamic and they are constantly in motion. So as a water molecule or some other type of liquid molecule is flowing past each other, there is a chance that one of these molecules will come into contact with another molecule and boop, bounce right outside of the liquid, break through the surface tension. Right, I have explained surface tension already in the form of Red Rover. There's always a chance that there's going to be one really energetic kid that breaks the line. And we can think of the creation of this vapor pressure in that same way. If there is going to be a really energetic molecule coming into contact with the surface, there is the chance that it has enough energy to pass through or to overcome that same magnitude for surface tension. Well, once the liquid is now outside or beyond the barrier of the surface, it's technically a gas, right? It's not bound to any of the other particles that exist above the surface. The more volatile your liquid, the more gas there will be present above the surface of the liquid. Now, in a closed container, like what we have illustrated here on the right, closed container, there will eventually be some type of equilibrium that is reached. You will not see an indefinite amount of evaporization, right? If that were the case, then no matter whether we had like closed bottles or open bottles, our like beverages would slowly evaporate. We don't see that. What we see instead is that there is a certain like saturation of gas that is met, certain saturation level for the gas above the liquid. And as the gas particles begin to build up, they're going to end up getting so close to each other that they will end up rebonding and then rejoining the liquid. So we may have some liquid turning into gas, but in a closed container, the gas particles will eventually bump into each other and then come back down into the liquid state. Returning to the puddle or spill scenario, we can see that this is not a closed system, but rather an open system where the surface is open to the atmosphere, it's open to the ambient air. Because there's nothing trapping the gas particles and forming them to, or forcing them to reform these connections, what the gas particles do here instead is just evaporate away. Well, if the particles here evaporate away, then there's going to have to be a new particle from the liquid that takes its place as a gas. And once that happens, it also is going to float away. And we see this exchange slowly over time. Maybe it takes a couple of hours, maybe it takes a couple of days, but assuredly all of this liquid will slowly turn into a gas just because of statistical chance, and then the gas, because there's nothing keeping it in place, is just going to float away. So in our closed containers, the liquids and the gases again reach this sort of equilibrium, this equal exchange. In an open system like the puddle, our water or our liquid will slowly evaporate away, and the rate at which it does is going to be proportional to how volatile it is. All right, but this isn't all, right? So this is the qualitative description of vapor pressure, and I did say we would be quantifying some things. Fortunately for us, we have already talked about gases and all of the gas laws, so everything that we have talked about in chapter 11 is still applicable to the gas that exists above the surface of a liquid. So inside of this closed container, there is going to be a gas present, and this gas will have a certain pressure. This gas will have a volume, this gas will have a temperature, and this gas will have a certain number of moles present. All of the gas law variables will be able to be applied to this system here to figure out something about the nature of this gas. That is exactly what Clausius and Clapeyron wanted to study. So not only were they studying ideal gases as a gas, but they were also studying gases as they interacted with other phases of matter, namely the liquids. All right, and here we come to two different forms, two different versions of what are known as the Clausius-Clapeyron equation. These equations on the surface look, I'm not gonna lie, a little intimidating, but what we're going to do is spend some time to talk through each of these variables. So let's talk about version 1 first. Version 1 takes the form of a y equals mx plus b line, where the y, or our dependent variable, is equal to the natural log of p vap, also known as our vapor pressure. So the pressure that is being exerted by the gas above a liquid, again known as vapor pressure, is going to be our dependent variable in this equation. In other words, we are looking to measure our vapor pressure as a function of what follows on the right-hand side of the equation. Next up, we have our m. This is our slope of the straight line, and our slope in this case is going to be equal to a negative enthalpy of vaporization. So here we see something coming back from chapter 10, enthalpies. Specifically, the enthalpy of vaporization here is the amount of energy necessary, to turn liquid to gas. So this is the amount of energy we need to cause our liquid to evaporate. This is going to be our term that quantifies how volatile our liquid is. The greater the energy, the more energy it's going to take to turn our liquid into a gas, and the lower the energy, the less it's going to take to turn our liquid into a gas. All right, underneath we see our variable r, or not our variable in this case, it is a constant. This constant r is the same gas constant that we saw in chapter 11. The value of the gas constant is going to be the exact same that we've seen before. Specifically, since we are working with energies in the form of enthalpies, the form that our gas constant takes is the 8.314 joules per mole Kelvin version. All right, our independent variable is going to be our 1 over T, aka temperature, is going to be the independent variable here. And last but not least, we see that there is going to be some measure of a y-intercept. In our generic equation, this is b. In our more specific equation, this is just a big constant c. Now, this big constant c is going to vary, and its meaning is a little bit more complicated than what we are going to be discussing in the scope of this class. So we're just going to acknowledge it for what it is, a constant of an intercept, and focus most of our time on the other variables instead. Namely, we are interested in the relationship between vapor pressure and temperature, as well as how volatile the liquid is as is being measured by the enthalpy of vaporization. All right, so if we're in the lab measuring a series of data points, vapor pressures versus temperatures, we can, as we have learned to do in lab already, plot the 1 over T, or the inverse of our temperature, versus the natural log of our vapor pressure on the y-axis, and see a bunch of data points forming a line here. We fit a line to this equation. The slope m is going to be equal to our negative change in the, or delta H, our enthalpy of vaporization, divided by R, and the y-intercept here is going to be equal to C. All right, so we can get some pretty cool information from the first version of our Clausius-Clapeyron equation. Namely, we can figure out experimentally what the enthalpy of vaporization for specific liquids are. All right, but before we move on, let's talk about the second version of the Clausius-Clapeyron equation. Instead of focusing on multiple data points, what this version instead focuses on is 2 measured data points. So this is more akin to the previous gas laws, like P1V1 is equal to P2V2, where we're picking out 2 specific data points to compare. Now, of course, the construction of the equation looks a little bit more complicated than our previous gas laws, since we have natural logs and inverses, but the sentiment is the same. So in this equation, we're going to be taking the natural log of the vapor pressure for one of our data points and dividing it by the second. This is going to be equal to the enthalpy of vaporization divided by R, multiplied by 1 over T2 minus 1 over T1. Notice that there is no negative sign here. That is not a typo. There is a plus sign now in front of our enthalpy of vaporization. This arises from how we actually worked through the math to derive this 2-point version of the problem or equation as opposed to the linear form. All right, so the second form of this equation is going to be most useful if you already know one of the data points. Let's say you've already measured, or there's a standard for one of the data points, and you want to know what the vapor pressure would be hypothetically at a different temperature, or you wanted to know at what temperature a different vapor pressure could be reached. And that's going to be exactly what we calculate now. So we're going to use the 2 data point version of the Clausius-Clapeyron equation, and we're also going to take advantage of knowing that the vapor pressure of water at 1 atmosphere is its boiling point, 373 Kelvin. And we're going to talk more about what that connection is in a couple of lectures. But using this information, we are going to calculate the vapor pressure of water at room temperature, 298 Kelvin. You'll also need to know that the enthalpy of vaporization for water is 40.65 kilojoules per mole, and again, the version of R that we are using is 8.314 joules per mole Kelvin. Now, I'm going to give you the chance to work through this problem on your own, but I do want you to be aware that the setup of the problem is not necessarily the hard part, right? Making sure your algebra is working out is going to be the tricky part. So this is another type of problem, sort of like the calorimetry problems in Chapter 10, that if your algebra skills are shaky, you will definitely need the practice to make sure that you are confident with this type of problem. All right, so please give it a chance, give it a shot, and we will come together and compare our work in a moment. All right, so I already said which equation we are working with, so let's just come together, solve this problem, starting with our Clausius-Clapeyron equation, natural log of P1 divided by P2. I'm just going to shorthand since we know both of these are vapor pressures. I'm just going to remove the vape from each of these variables for saving a little bit of space. This is equal to our enthalpy of vaporization divided by R, multiplied by 1 divided by T2 minus 1 divided by T1. So we have different temperatures, different pressures. We're going to take these data points, or rather take the information from the wording of the problem, plug this in, rearrange, solve for pressure. All right, so first things first, we can see that we are given data pertaining to one of our points. We can assign this information as either 0.1 or 0.2. It does not matter. Just so long as these are both considered to be 0.1 or 0.2, your algebra should work out. So I'm going to assign this data as being equal to number 1, point number 1. So I'm going to insert our 1 atmosphere here in the numerator. P2 is going to be the variable that I am solving for. This I will be considering then the vapor pressure of water at 298 Kelvin. All right, we're told that the enthalpy of vaporization for water is 40.65 kilojoules per every mole, and our gas constant R is 8.314 joules per every mole. So we want to make sure first and foremost that our units again are working together. This is always going to be an aspect in every quantitative problem to make sure that the units work together. So we need to make sure that either the kilojoules get converted into joules or the joules get converted into kilojoules. I'm going to do the latter. So 8.314 joules per mole Kelvin is equal to 0.008314 kilojoules per mole Kelvin. All right, time to insert some temperatures. T2 is going to be my second data point, so this is going to correspond to 298 Kelvin, and we're going to subtract out 1 divided by 373 Kelvin. So now we can see we have everything set up, one equation and one unknown to solve for. What makes this problem, as I hinted at or explicitly said earlier, is the algebra. Namely, we need to solve for a variable that is inside of a natural log. All right, so we'll walk through how to do that, but first I just want to simplify everything on the right-hand side of the equation. That's going to be my first step. So if I work through the math, 40.65 divided by 0.008314 times our temperature thing on the inside of these parentheses, all of this works out to being equal to 3.30. Question number 1, does this number have a unit on it? Well, let's come and inspect all of the units that were in the bulk of the problem. It looks like kilojoules cancel here, moles cancel here, and kelvins all cancel here, because if you take a Kelvin minus a Kelvin, you still have a Kelvin, but the kelvins cancel out overall, so it looks like this 3.30 is unitless. This is actually a really good thing, because as we start working to remove this natural log, we are not going to want a unit to be present on the 3.30. The other way to solve this problem, again, where we have the natural log of 1 atmosphere divided by P2 is equal to 3.30, is to take each side and raise it to the E first. So if we take our natural log of 1 atmosphere divided by P2 and raise that into the exponent of E, same thing with our 3.30, what we find is 1 atmosphere divided by P2 is equal to 27.11. Now from here, in order to rearrange and solve for P2, it looks a little bit more familiar, it's a little bit easier. All we have to do basically is take the inverse. P2, I'm gonna come up here to give myself a little bit more room. P2 is going to be equal to the inverse of 27.11. That's how our algebra ends up working out. Atmospheres, of course, is our units, and we find the exact same answer, 0.0369 atmospheres. All right, but now that the problem is answered, we can actually address what this means. We have a way to predict what the vapor pressure of water is at any temperature, and it just so happens that at room temperature, the pressure of the vapor above the surface of a liquid of any species of water is 0.0369 atmospheres. All right, so we come to the end of our first section of chapter 12. Within, we discussed liquids. If you have any questions or concerns on anything that we have talked about thus far, specifically any of the properties and how they are connected to the intermolecular forces within the liquid, or if you have any questions on the Clausius-Clapeyron equation and making sense of vapor pressure, please do not hesitate to let me know. If you have homework, please double check and do your homework, and until next time, class is dismissed.